Okay.
You see my screen? You see my screen?
Yes.
Okay. Today I will talking about the phone system with the ammeter. As we can see over here is the PCT connect to the rectifier and then connect to the bus converter. And then we fix restore is equal to the 1.8 voltage. And when we train the TP and TN according to the VLAN. Uh, After the from the VLAN, which is the connect to the reference later. And then after uh, through the representator, we have the VREF output with the approximately 1.8 voltage. We can train the V0 to the V5, V3 is the 4 bits. To train the VREF to the VREF output is the approximately 1.8 voltage. After that, we compare the VREF output to the V storage. So we have a two output. If the VREF output is higher than V storage, the output speed is higher. And then if the V storage is higher than the VREF output, the output N is higher. So we connect the output speed to the full speed control. As we can see this slide, I connect the output to the full speed control and control by the V0 to V3 is the 4 bits. So we have the two outputs, either NT and the PT. Is the because we use over here is the 1.8 voltage, so it's cannot control the P the MOSFET over here because we use the 5 voltage MOSFET. So we need to have the level shifter for the NMOS and the PMOS from the storage. Is a 1.8 voltage to the readouts to control the two MOSFETs over here. And then it's connect to the buffer for NMOS and the buffer for PMOS before connect to the MOSFETs in the TP and the TN.
Wait.
Uh,
Your power control should be connected to V-store, right? Power control.
Restore.
The this power
I
control.
connect to the output speed and the
No.
V0 to V1.
The VDD for power should be V-store, isn't it?
Oh, I missed.
Right?
Let me check. I do not remember.
Can you open schematic?
Okay. Is the full bit control. This is
VDD should be V-store, right? It not V-rack.
oh, it's going to be sorry.
Right?
Okay.
So only after level shifter, before level shifter, all the circuit is powered by V-store 1.8 volt, right?
Okay.
Okay.
This is my system over here.
Yeah, just after level shifter. Right, before level shifter, all the circuit is by V-store, powered by V-store, and then level shifter will shift all the voltage from 1.8 volt to VRAC, right?
Okay.
Okay.
So, and then I use some example is the three example. And the first one is the n equal to 0. So we have a 4 bits either 0, 0, 0, and 0. So we can have, as we calculate that's the Vref is approximately 2 voltage. And then we start the figure 1.8 voltage. And as I calculate the TP, the duration of the length of TP is approximately 700 nanosecond, and the TN is approximately 18 nanosecond.
But in the stable state, here Vref should be 2 volt, right? In the stable state.
Yes,
Now,
because
now here is the beginning of the circuit, right?
yes,
Vref will
because
decrease. Yeah.
yes, because I run this, but it take a lot of time, so I just run about 300 microsecond. So
Yeah,
it's
you should
fluctuate.
run long time to see to check your efficiency. You should run like my case, right?
Okay, okay. So to another example, it is 7, yeah, and the equal 7. So we can calculate that the for this the 1110. So we have the direct is approximately 3.4 voltage, and I also calculate the TP and TN over here.
3.4. So
Yes,
2 plus 0.2 multiplied 7. All right, 3.4, right?
yes. And another example is n equal 15, so we can have the rate with approximately 5 voltage.
Vref.
Yes, I will run more example for the next time.
So TP and TN, is it correct?
I calculate over here is the PD and the
TP should be how much? TN?
oh no, sorry, I don't I don't measure the TP and TN, and I measure the NT and PD.
What?
I measure the over here NT and the PD, not the TN and TP. Commonly the
Yeah,
same.
they are the same, only
Yes.
different voltage, right?
Okay, okay.
So
Over here is I can zoom out with the 15 is the TD is the 100 microsecond, and the TN is the approximately 370.
300 nanosecond,
Yes, nanosecond.
and here is 500 nanosecond, right? No,
200.
no, it in the middle.
Sorry. Approximately 500 nanosecond is the 400 and the 96.
Wait. So when Tn is equal 1 plus NTD.
Yes.
So one plus NTD and 9 TD. So TP is 9 TD. How much is 1 TD?
Let me check. I think it's approximately 78. 78.
should be 700. TP should be the same, right? With
Yes.
my case, T will not change, right? TP.
Yes.
But in here, TP, your case change, isn't it?
Yes. 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 Oh,
I think it's because your power width control power by VRAC. Your VRAC change,
yes.
so the delay will change for the VRAC.
Okay.
Right.
Let me change to VStore. Okay.
Yeah. If VStore fixed, so your delay will be fixed, but delay will change with the VDD. So in your case, wrong.
Okay.
But let's check. Now TP is 9 TD, right?
Yes.
TP is 300 nanosecond.
Yes.
370 nanosecond. Right?
Yes.
And TN now should be 1 plus 7. It's 8
1+7. Okay.
TD, right?
Okay.
Now TD should be 8 TD.
Actually. Okay.
TP 9 TD, but TN is just 8 TD. Why TN is larger than TP now? Right? You should check, isn't it?
Okay. Okay. Okay.
So your TN and TD is wrong, right? Compared to
Yes.
the thesis calculation. You should calculate by your own and then check with simulation. Now it looks like your simulation is wrong with TN, right? Let's check.
Yes. Okay.
Next.
So it's the end of my presentation. I will fix the another example also, but check the TP and TN.
Let me you are showing wrong. Let me share my screen.
Okay. Okay, I see your
My
screen.
screen. Here you showing n equal 15 is not 7. Your 7K is here. So in here, TP is how much? TP
It's
nanosecond. And TN is plus n, right? Plus n is 7. Is correct, TD? So 1 TD is how much?
LTD is 18 Let me check.
It's, yeah, it's quite correct, right? It's correct. If we calculate here, TD for
46.
if we calculate TD from here, so yeah, it's almost similar. So yeah,
Okay.
your circuit is correct, right? How about this case? In this case, and here it should be 16. How much is 16 to be here?
One 500 was 63.
Yeah, it's
Oh, sorry. Oh, yes. Okay.
it, so it's about
Let me check.
more than 10% different. So you should check.
Okay.
Right? It's more
Okay.
than 10% different. You should check your delay circuit again. Okay?
Yes.
Okay. Right.
Yes.
Share your screen.
Yeah. Excuse me. You can see my screen, right? So I just like corrected the previous week's. I just correct the previous week's like.
No, I don't see your screen. I have to stop. Okay.
Yes, I see.
Okay.
Okay.
Yeah.
So I just corrected the mistake of the previous week. So here. So for the reference ladder, I did not include the VREF 0, 1, 2, 3 because I didn't understand them before, but now I did, and like here are like this. So these works like beats. So if we see this slide, so VREF is 2 plus 0.2 times n, where n is 0 to 15. These are 4-bit binary number, and those 4 bits are 0. This VREF 1, 2, 3. So if x is equal to 4 mega ohms here, and different depending on the VREF values, the resistors are activated or deactivated. For example, if n is equal to 4, then it is 0, 0, 1, 0. So this 8 or 8 mega ohm resistor will be activated and the others will be deactivated. For example, here the example shown, sorry, n is equal to 3 here. If n is equal to 4, then this will be 5 and the other will be 0. So for example, n is equal to 3, that means 0, 0, 1, 1. So we have this and this to be 5 volts and this to be 0 volts. So these two resistors are out. Only these two resistors, is 8 mega ohms and 4 mega ohms resistors, are actually activated. And this is how it works. And there are multiple test cases. Test case 1 is equal to 15. So all of them are equal to 5 volts. And if we see the V out in data, we can see that V in is V rate is 5 volts and V out is actually pretty close to 1.8. You can refer it is exactly 1.8, 1.805. Then if n is equal to 1, if n is equal to 1, then VREF is equal, this is 5 and the others are 0. And indeed, we see that the V out is 2.2 because 2 plus 0.2 is 2.2, and the output is exactly 1.8 volts, as you can see. Test case n equals to 3, so these two will be 5 volts, this two will be 0 volts, and VREF will be in that case 0.6 volts. And indeed, we see that for 0.6 volts is the VREF, and the V out is at exactly 1.8. Then with the pulse width control, so pulse width control, before designing the pulse width control, I designed the delay circuit, which looks like this. And then I designed the symbol and the parameters below, and then this is the output it shows. So for this particular configuration, n is equal to 20, and this particular configuration, it gives exactly 26 So I can just connect these three in series to get a 28 nanosecond delay circuit. So this is how they look like. And indeed, I can see that you can see that the delay is almost 78 milliseconds. Sorry for the title. So, and this is the schematic for the switch control circuit. So here it is. I deleted the this part. So the changes I did is that like the AND, NOT, MUX, and MUX circuits all are now taken from this 2-volt library instead of the 5-volt library, and I use my own the circuit that delay circuit delay cell that I made of my own. This is the parameters, and this is the output that I get. So for the poor del, the positive delay, this is the time difference that I get, which looks like this. As all the delay circuits are on, so like all of the 16 delay circuits will be on in that case, and this is the delay that I get. And this is the negative delay that we get. So 9 delay circuits there. Finally, level shifter circuit. So this schematic looks like this. So I highlighted this MOSFET because in this MOSFET, this voltage was previously V star, but if it is V star, then actually the MOSFET does not turn on, and that's why the result is wrong. So I changed it to VRECT, and indeed the result was correct, and you see the VIN the amplitude is 1.8 volts, and the output amplitude is 5 volts. Thank you.
Okay. So
Actually, I just wanted to show something else.
you have issue
Yeah.
with issue. So in my full full circuit schematic. So this is the full circuit schematic. I have fixed the delay cell, so it should be all right now. But when I'm trying to get the graph, so this graph here, so the TP and TN graph looks like this. And if I actually see the time difference here, 5 microseconds. Let me control your computer.
Yeah, sure. You should be able to control my computer. And there is something else I want to show you, but before, let's just fix it first.
Why you only make 5 microsecond?
As I said, like I fixed like my delay circuit for this configuration that for 5 microsecond and n equal to 20, it gives the right delay, and that's why. I mean, you said it should be bigger than 6, so I gave it 10. It should be okay.
Are you touching your computer? Don't control.
No, I'm not.
Why here? Net 19 is, it should not be.
Oh, by the way, here.
What?
In the pulse width control, can you go back? Yes, here there are like warnings. I don't understand why. And there was no warning, but after I fixed the delay circuit and then tried to test it, it certainly started giving warning.
Why is VDD? Why is VDD? What is VDD here? Did you set VDD? In here. It should be restore internet, right? In here, you doesn't set any VDD here.
Okay. Wait, can you go to the
So when you copy one schematic to other schematic, remember the name of VDD you made for it. Okay.
Okay. Wait, can you go to the ADL? Can
So
you go to
there's one quick change. I can change all your VDD to VStore pass by add pin VDD. Okay. Add pin VDD, and then you change to here VStore. Okay. All your label will change to VStore.
Okay.
Let's run. Remember, when you copy one schematic to other, always check the label name.
Okay.
It is correct now.
2 seconds. I mean, n is equal to 1. Can you check the Tn? I mean, Tn is bigger than T2. Not the case.
Did you check your schematic, your delay?
Yeah, sure. Yeah, I checked and like fixed the delay circuit.
You simulate with 1.8 volt.
Yeah. 1.8 volt, 10 micro CL. The clock is equal to 10 microseconds. I mean, everything same. N equal to 20. Exact the same condition, and it gave right result.
So how much TP should be in here? How much in your simulation?
TN should be 77, and the TP should be 2 times 77.
What?
2 times 78. N
In,
is equal to 1 here.
in here 9 TD, right? How much is 1 TD? 9
TD is 78.
78 nanosecond.
Yep.
So it should be 700 nanosecond.
80
right?
nanoseconds. Yeah, 780 nanoseconds. Yeah, 700 nanoseconds.
In here is almost double, 1.4.
Yeah.
It's idea. I see that the voltage the V1 to V0 to V3 is not on almost zero. Is the have the one is a one voltage is a 5 voltage.
Where?
It's the ATL. Ideals.
The ADL,
Parameter.
the parameters. Yeah,
Yes,
yeah.
yes.
Where?
That is the VRAP 3 is a 5 voltage.
Yeah.
That's right.
5 volt? Yes. What problem?
By the efficiency value, can I see the efficiency value?
VRAP doesn't make sense in here, right? In TP.
Yeah.
TP should be
I mean,
fixed. VRAP
Yeah,
is,
it doesn't depend on VRAP.
yeah, VRAP
Well,
is,
actually, it does because here.
it only change TN. TP, your TP fixed.
Okay. Makes sense.
Here is the delay of TP fixed. So don't make they connect to, you should make some space to check. one delay is this. Open your delay circuit. I want to check.
Okay. Whether time is not left to be like rejoin.
Yes. Open the test band for 26. This 26 nanosecond test band.
Opening the test band.
This delay cell.
Yeah.
Where your test band to run to check the delay.
Oh, okay. Okay.
The test